Ladies and gentlemen, hello, welcome, coming to you not quite live from One Take Studios, where today we are looking at right triangle trigonometry. Believe it or not, there's trigonometry that does not deal with right triangles, but this is the foundation for all of that. Some of you may be thinking, I know everything about trigonometry. I guarantee you do not, and I might even surprise you with something today. Alright, but we are going to start with things that hopefully are relatively basic or foundational at this moment. Trig functions. Trig is short for trigonometry. That's our affectionate name for these things. Trig functions are simply rules based on ratios comparing sides of a triangle, specifically a right triangle. What does this mean? Alright, that means that there's right triangles in life. They happen. There we go. There's a lovely one right there. And somebody started paying attention. That every time I've got a certain angle measure, my sides, when I stack them, when I turn them into ratios or fractions, I end up getting the same values over and over again. Alright, so that's where these are coming from. Now, what the heck is that? Alright, so a couple of things that we need to establish here. First of all, it does have to be a right triangle. There's my right angle. But this right here is our perspective on things. This is a Greek letter. This is known as theta. T-H-E-T-A, theta. Kind of looks like a zero with a line through the middle. Sometimes reminds me of an Easter egg. I also like to refer to it as a "you are here" sign. None of this can be done without perspective. And if I don't know where I am, then I don't know what perspective to take. And so this is my "you are here" sign. So if you are standing right here, now we can all of a sudden name the relationships of the sides around us. Hopefully you've heard at least before that the longest side of a right triangle, the side that is across from the right angle, is known as the hypotenuse. Hypotenuse. That one will not change its name. These two, however, are flexible based on your perspective. The word adjacent means next to. If you are adjacent to something, you are next to it. Well, if I am here, which side is next to me? You could argue that the hypotenuse is, but since it already has a name, what's the other side that is next to me? Right here, this is it. I'm going to call this the adjacent side because it's next to my theta. It's next to my "you are here" sign. Adjacent. There we go. Alright, well also then if I'm standing here, what is across from me would be the opposite side because it's on the opposite side of the triangle. So this is going to be the opposite leg of my triangle. Alright, so hypotenuse is fixed. These two, depending on your perspective, depending on where you are, if you are here, this is opposite, this is adjacent. If you are here, this is opposite, this is adjacent. So that sign actually makes a difference. Theta is going to be an acute angle, it's not going to be your right angle. At least for now. Ha ha ha. Alright, things that you may have heard before and think you know. Would include fun things like, if we leave this as a point of reference for ourselves here, sine. There we go, better picture. Sine, S-I-N-E, that is how it is spelled. It is abbreviated S-I-N. If you would like to sound intelligent at all, you should not call it sin. You should call it the sine of theta, even though when we write it, we don't write the E. Now notice I put the sine of theta. Sine is kind of like an operation, sort of. It doesn't stand on its own. There has to be something after your trig function. So I wrote theta, because it's referring to my angle. Theta is a variable. I could put sine of 20 degrees if I wanted to, and that would be okay too. But what we're saying is I'm taking the sine of a particular angle. So I don't get to have nothing here, so don't get lazy. Put theta, put x, put something, put an angle measurement, whatever you like, but there's got to be something there. Sine is what I get when I take the opposite side over the hypotenuse and I stack them. So every single time this is 20 degrees, when I go with the opposite side over the hypotenuse side, it makes a specific fraction. The triangle can be bigger, smaller, doesn't matter. Every time this is 20 degrees, the relationship between these two sides is going to form the same ratio. Hence, these are our trig functions. We also have cosine. Cosine is spelled C-O-S-I-N-E, but abbreviated C-O-S. Again, you will still say cosine of theta if you would like to sound intelligent, which is going to be the adjacent side over the hypotenuse. You may have heard that one before. And then the third one, do you know it? Is tangent. And ladies and gents, there it is. All right, so again, TAN is our abbreviation, tangent is what it's called. The tangent of theta is the opposite side over the adjacent side. So again, depending on where you are, all these are simply fractions that show the relationship between two out of the three sides of our right triangle. A lot of people go with SOHCAHTOA. to remember that. That is fine. People tell stories about that sometimes. I'm not going to do that. But what you can see here, hopefully, is SOH. Sine is opposite over hypotenuse, SOH. Cosine, then, is adjacent over hypotenuse, so CAH. And TOA, TOA, tangent, is opposite over adjacent. So that can be a nice memory device for you. However, did you know that there aren't 3 trig functions? There are 6 trig functions. Ah, you might not have known that one, huh? So what are the other 3? Well, let's see. Ladies and gentlemen, the other 3 are reciprocals of the first. Sine's reciprocal is called cosecant. Cosecant. And its abbreviation is going to be CSC. CSC, cosecant. And let's see, that's going to be, again, of theta, cosecant of theta. And if it's the reciprocal, we are truly flipping this over and calling this the hypotenuse over the opposite. There we go. All right, so now we have 4. And again, each of these other 2 originals also has a reciprocal. What is cosine's reciprocal? It is secant, the only blind trig function that we have. Secant. Abbreviated SEC, again, the secant of theta equals, and again, we're just going to flip this over then because it is the reciprocal. So this is going to be hypotenuse this time over adjacent, ADJ, there we go. All right, and then last but not least, tangent's reciprocal is the easiest one to remember the name for, and that is going to be cotangent. Cotangent, abbreviated COT. So the cotangent of theta is equal to, and again, flip it over, adjacent over opposite. So there are actually 6 trigonometric functions. That's a fun word, say that, trigonometric. All right, so if I can get these 3, I can get these 3, but just by flipping them over. The hardest part is remembering which one is the reciprocal of which. Tangent and cotangent, again, those are kind of obvious as far as the relationship goes, but for example, sine and cosine are not reciprocals, and secant and cosecant are not reciprocals. So how do I remember that sine goes with cosecant and cosine goes with secant? I only have one thing for you. It's dumb. If you don't like it, I don't care. It works for me. Ready? Here we go. The cos don't go. That's it. That's all of it. The cos don't go. That helps me remember that cosine and cosecant can't possibly go together. Therefore, cosine must go with secant, and sine must go with cosecant. If you can do better, do better. That's all I got for you on that one. All right, so what are we going to do with this mess? Well, let's keep these guys where we can see them. And, oh, look, it's another triangle. And, hey, it's a right triangle. And the directions for this triangle say, find the exact values of the 6 trigonometric functions. Okay, we know what the 6 trig functions are. We need their exact values. Please note the word exact. Trigonometry is kind of got one foot in the old school stuff. And so while you can get decimal answers for these ratios, if they ask for exact values, you can't go with the decimals. You got to go old school, reduced fractions, watch out for radicals. Oh, why would I say that? Well, let's see. If I'm going to create these ratios, I need to have all 3 sides. Oh, can't do the problem. I only have 2 sides. But there's the Pythagorean theorem. Yes, you said it. A squared plus b squared equals c squared. We can actually find this. So we are saying that 7 squared plus 4 squared would equal our hypotenuse, side c squared, which is going to be a grand total of 65 equals c squared, but I actually would like to know what c is. Therefore, I'm going to take the square root of each side. So what is the length of my hypotenuse? Sad but true, the square root of 65. And because we're going for exact values, we're not going to go with decimals right now. We're going to call it the square root of 65. Painful, but it's okay. We can do this. All right, so I need all 6 of these. So let's start with sine, because why not? Just to make sure I get enough space, I'm right over here. Sine of theta is equal to sine of theta. Ooh, theta, you are here. And sine is going to be opposite over hypotenuse. Opposite of me, if I am here, is 4. And hypotenuse is the square root of 65. So this is going to be 4 over the square root of 65. Can I leave it like that? Nope. Why not? Because I'm looking for exact values. This has a radical in the denominator, and I'm not allowed to have a radical in the denominator. However, shall I fix this problem? What will make a square root go away? Creating a square. The first time you see this, it's hideous, and then it gets much better after that. All right, so if I'm looking at this, that's going to give me 4 times the square root of 65 on top. I'm going to write it a little bit larger here. 4 times the square root of 65 on top over the square root of 65 times the square root of 65. That's a square and a square root undoing each other. That's just 65. Ladies and gentlemen, that is the exact value for the sine of theta based on this triangle right here. That was exciting. While we're at it, sine, cosecant, right? Can I squeeze this here? You're probably thinking it's not going to fit, right? However, if cosecant is the reciprocal of sine, let's flip this over. Yeah, but let's be smart about it. If I flip this over, I'm going to end up with the square root in the bottom again. Let me go back to my original. What happens if I flip this one over? I will get the square root of 65 on top, and I will get 4 on the bottom. That's an exact value, and it doesn't have a radical in the denominator, so that one is actually done. So again, some of these take a little bit more work, and some of these take definitely less work than that. So what does that mean about the cosine of theta? Cosine of theta is going to be something similar, adjacent over, and so this is going to be 7 over the square root of 65. Again, if I think about what happened on this last one, I can multiply top and bottom by the square root of 65, giving me 7 times the square root of 65 all over 65. You do these often enough, you see the patterns, you know where they're going. So there's my cosine exact value. And then cosine's reciprocal is secant. Flip it over. Secant of theta is equal to, flip the first one over if we're smart. That way we've got the radical on top where we would prefer it to be, over 7, which is on the bottom. And now we are 2/3 of the way done. We're trying to get 6 trig values. We have 4 trig values. That leaves us with tangent. Let's see, tangent of theta for this one. Tangent of theta is going to equal tangent opposite over adjacent. Ooh, that's not bad at all. That's just 4 over 7. There's no radicals, and that's simplified. That's it. Rejoice. Cotangent is the reciprocal, which is equally rejoicing, because if I flip that over, that's 7 over 4. Ladies and gentlemen, the ratios, the fractions, are the trig values. We have just found the trig values. We have not found any angle measures right now, and that's okay. But if they're asking you about trig values, they want these fractions. All right? If you have a teacher or circumstance that allows you to do decimals, great. But so often for these, especially like even on standardized testing, they want you to be able to do these fractions and do your reduced radicals and simplified, all that kind of fun stuff. All right? Okay, so we got that. And then I drew you a picture. Okay, here's your picture. Oh, look, it's you. You're going for a walk. That looks like fun. Lo and behold, on your walk, all of a sudden something appears in the sky. Whatever could it be? I have no idea. What is that? Oh, look. It's Mary Poppins! Wait a minute, but how on earth are you going to be able to see Mary Poppins? Because she's way up here and you're way down here. Ladies and gentlemen, that is easy, all right? From the eyes that are in your toes. Yes, I just said that. From the eyes that are in your toes, you are going to look up at Mary Poppins. Does it bother anybody else that you've got a chick in a skirt floating through the sky? All right, she needs to have bloomers on. I'm putting bloomers on. That way we can't see up her skirt. Excellent, much better. Now, if Mary Poppins is going to see you, she was staring off into space, trying to make sure that she doesn't hit any pigeons on her way through. And instead of staring straight out, she's going to look down to be able to see you. Why do I make this point? Oftentimes when we are setting up problems for trigonometry, there are a couple of phrases that come into play. This angle right here from the horizontal looking up is called the angle of elevation. Angle of elevation. And if you see those words, you need to know what they mean. Ooh, I can spell elevation better than that though. Elevation. There we go. All right. Now, on the reverse side of that, this angle right here, Mary Poppins again was looking horizontally, now she's looking down. This is called the angle of depression. The words themselves are kind of helpful as well. Both start off from a horizontal perspective. Elevation goes up from the horizontal, and depression goes down from the horizontal. All right, so things to keep in mind, just in case you have a problem like this one. Oh, look. A ramp is 10 feet long and has a 12-degree, ooh, we actually have a measurement this time, a 12-degree angle of elevation. What height will the ramp obtain? That sounds like a triangle to me. Imagine that. So here's a delightful triangle. Is it drawn to scale? No. Do I care? No, that's okay. I just need something to help organize my information here. Here's my right angle. What boggles my mind is that I've got people that don't know which of those three sides is going to be the ramp. Which ramp would you want to be on? The one that runs you into the wall, the one that runs you vertically, or the one that actually has a gentle incline? Yeah, ladies and gentlemen, this one is the ramp. That is 10 feet. And angle of elevation goes from the horizontal, and we are looking upward to see Mary Poppins, so the 12 degrees goes right here. I actually want to put the degrees sign with it because if I don't, it means something different. And the further you get into trigonometry, the more meaningful that becomes. If you don't have degrees on there, it means automatically you are doing radian measurements, which you may know nothing about at this time, and that's okay. All right, so what would let's see, the height, that's going to have to be this guy, right? If I look at my 6 trig functions, I'm going to say which one of these is going to be the most helpful to me to find the height of this ramp. How high will the ramp go? You are here. I know this to be 12 degrees. I don't have the opposite side. I do have the hypotenuse. Opposite hypotenuse. Oh, sine. Sine seems like a very fine choice here, because if I go with the sine of, again, remember that theta was a variable, stands in for an angle. We don't need the variable because we know the angle is 12 degrees. The sine of theta, sine of 12 degrees, is opposite, x, which I don't know, over hypotenuse, which is 10, and I do know. Cool. All right, now, something that you need to be aware of, let me switch my screens here and take a look at this guy. All right, ladies and gents, if you are going to be pressing trig buttons on your calculator, you need to pay attention. All right, I'm going to my home screen right now, and I am looking at settings. All calculators have this someplace if they have trig buttons. If I look at document settings, right now for angle, it says degree, because I changed it. When I turned it on, it actually said radians, and I want it to be in degrees. Does it make a difference? Yes. Yes, it does. All right, so degrees is nice, there we go. Okay. If it's not in degrees, please make it degrees, and then we can go from there. All right, so I'm going to go back into my current document that I've got going here, and I would like to find out what the sine of 12 degrees is. Well, I'm looking for my trig buttons, and where might they be? Oh, look, there's a button that says trig on it. I bet you that's useful. Trig, there we go. All right, ladies and gents, here is all 6 of my trig functions, the little dudes with the negative ones there. Pay no attention to the man behind the curtain. Those we will be talking about later and not today. All right, so sine of 12. I can't put the degree sign here, and that's okay because I just told the calculator, hey, we are in degrees. And that has a value of 0.207. So anytime you are using sine, cosine, tangent, or their reciprocals, please check the settings of your calculator. They will give you the wrong answer if they are in the wrong unit of measurement. So flipping back 0.2079. So if we go back to this guy, we just found out that 0.2079 is the value of sine of 12 degrees, and that equals x over 10, and if I multiply by 10, hey, I could find that out. So this height of this ramp ends up being 2.079. Probably, feet, yes, there we go. It's in feet. Ta-da! There we go, that's how high it goes. It's not a very strong incline, so that makes sense. Okay, so there's a lot of things here. Pay attention, pay attention, pay attention. All right, details, practice, eyes peeled, know your vocab. Okay, have fun with it.